Hello, and in this video we're going to be looking at the length contraction or the Lorentz contraction of objects that are travelling at relativistic speeds. So basically what that outlines is that when an object such as a train, as we've got here, travels at speeds close to the speed of light, the length of that object starts to contract and get smaller. Now if you were on the train and the train was travelling at say 0.9 the speed of light, you would still think the train was the same length. The train wouldn't contract, you wouldn't feel it, you wouldn't see it. The length contraction is as observed by someone stationary. So a person standing at the side of the track watching this train go by would see it smaller. So we've got a little bit of a problem. We've got a train, and this train is 100 metres long. And this white block here is my attempt to represent a tunnel. And that tunnel is 50 metres in length. And as you can see, no matter what you do to the train, no matter where you put the train starting off or finishing, the train never quite fits into the tunnel. Classical mechanics says that as it is completely impossible for that train to exist inside the tunnel. However, it is possible. So how do we go about working that out? Well, there's two terms that we need to know, L and L0. Term L is the length of an object as seen by a stationary observer. Okay, and L0, if you like, is the proper length, and that is the length of the object as viewed by someone who is stationary to the object, who's moving at the same speed at the object. So if you were on the train, you could measure the train and you'd find the train was 100 metres in length, no matter how fast the train was going. Okay, and this L, just L on its own, that's the length of the train as observed by someone who is stationary. Not stationary compared to the train, someone at the side of the tracks. Okay, hope that makes sense. So where do we go from there? We know that L equals L0 over gamma. Okay, we can do a little bit of rearranging, make gamma the subject, and we get that. Now we know what the proper length of the train is. That's 100 metres. Okay, and we're aiming to get the train to be 50 metres long as observed by someone standing at the side of the track, standing next to the tunnel. So our length L is 50 metres. I'm going to simplify that down a bit. So gamma equals, what should we say? It's 2 over 1, 2 50s and 100. So I'm just going to call that 2. It makes the math just that little bit easier. So what do we then need to do? We're trying to work out how fast this train needs to be going. That's effectively what we're doing. We're finding what gamma is. So let's write in what gamma is. That's 1 over the square root of 1 minus v squared over c squared. Okay. I'm going to substitute in for v squared and c squared this term here, beta, and beta is v over c, so I can rewrite gamma as 1 over the square root of 1 minus beta squared. Okay, and we'll do a little bit of rearranging here. I'll bring that up to the top, 1 minus beta squared equals 1. What I'm then going to do now is I'm going to bring this gamma down underneath the 1 here, and I'm going to square everything to get rid of the square root sign. So I'll scroll down just a tad, and then we'll do that. So I'm bringing the gamma down underneath the 1, which will leave me with 1 minus beta squared, square rooted, but remember I'm squaring everything as well, and 1 over gamma squared. Square that, bring it down to here, divide by gamma on both sides, or gamma squared. Okay. Next step. I'm going to bring gamma the 1 over gamma onto this side. So I'm going to take 1 over gamma squared away from both sides. So that'll leave me with 1 minus beta squared minus 1 over gamma squared equals 0, and then I'm going to add beta squared to both sides. Okay, so beta squared is going to equal 1 minus 1 over gamma squared. Let's get rid of that square root. So beta equals the square root of 1 minus 1 over gamma squared. At this point we know what gamma is. This is a kind of nice point to put that in. Maybe gamma's 2. Remember that from all the way up here. So I'm going to put 2 into that equation there. So beta equals square root of 1 minus 1 over 4. So the square root of 3/4 is effectively what we're after. And that is equal to 0.866. And so let's remind ourselves now what beta is equal to. Beta is equal to V over C. Now remember, we want to know how fast the train needs to go for it to fit in the tunnel. So V equals beta times C. So the velocity of this train is 0.866 c, or 0.866 times the speed of light. There we go. And if the train was going that quickly, 0.866 times the speed of light, the train would actually fit into the tunnel. So if you were the stationary observer, what you'd see happening is the train shrinking like this to such a length that it would completely fit inside the tunnel like that.